Hi, I'm Alex Kreese here at Markforged, and today we're going to be talking about an overview of designing for additive manufacturing. Design for additive manufacturing is a subset of designing for manufacturing, which basically means adjusting your design to make it cheaper, faster, or more effective to manufacture. Executing proper design for manufacturing techniques can increase yield and save time and cost when building your manufacturing process. As an example, when you design a part for CNC milling, there are a few things to think about. Things like your mill's make and model, capabilities, and its working volume are all machine-driven. High tolerance features, tool changes, and setups are all part-driven. Beyond that, there are details like spindle speed, materials, and tool type that further impact the manufacturing process. If you have a complex part, it's easier to make on a more complex machine, but those machines are more expensive. A well-designed part makes use of the manufacturing technologies at hand to simplify and streamline its production. So this can involve minimizing tool changes and setup time, adding features to make indexing easier, and more. Some of these are machine-specific, and some of them have to do more generally with the manufacturing process and the material behavior. Now, designing for 3D printing is similar, in that some aspects are process-dependent and some are printer-dependent. You can get lost in the details of specific practices like overhangs, feature size, layer resolution, things like that. These are all highly printer-dependent, and we won't cover those right now. What we're going to do is focus on design for additive manufacturing from a very high level, highlighting what unique advantages it brings to the table and how you can use it to make a functional part. 3D printing being an additive versus a subtractive process opens up a wide range of design opportunity, but also comes with its limitations that should be accounted for in your design. First of all, 3D printing is a layer-by-layer process. Cross-sections of parts are extruded on top of one another to build up your model, which uncovers one of additive's biggest advantages. A complex part is just as simple to set up as a basic one. Let's take these two designs as an example. A simple part with a vertical hole like so requires a simple machining setup if you were to be milling this, whereas an angled hole requires either a more complex machine or a more involved fixturing setup. When you 3D print the same two parts, you just send your part to the 3D printing software and hit go. The printer does all the setup for you, so a geometrically complex part takes the same amount of time and effort to set up as a simple one. One of the drawbacks of a deposition-based plastic printing process is that the parts are anisotropic, so the material strength will be different along planes parallel to the print bed than along the axis that's normal to it. Think of it like a stack of Post-its. It's hard to break this way across the surfaces, but it's easy to pull apart at the seams between the discrete slices of material. So with additive, it's important to put thought not into just a part's printability, but its performance and how it meets your functional requirements. What about your part benefits from 3D printing? Which features add value when printed versus made in other ways? We can sum it up with this example here, a simple tetrahedron shape. The first iteration of this is a basic kind of blocky shape. It works, but it's basically like a block CAD model. It's easy to get to this stage, call it good, and hit print. This right here is a 9-hour print and costs $12.63. Say we expect to go through multiple copies or revisions of this model, we may want to make some improvements. So to save time and cost, we can reduce the print time by doing something like this. We cut out a lot of the material in the center, but maintain the structural integrity of the part with ribs instead of a solid block. So this print here takes 6 hours and costs $6.12. But from a structural standpoint, this part is anisotropic. When we apply a load to this part, it can shear along the layer lines. So let's take a step back here for a minute and talk about the requirements of this part. What's important here? We care about the strength, since this may need to endure a large load, and we also care about these angles here to make it a regular tetrahedron. So these angles are complex geometries that need to be precise, and the part can't break on these beams here. If we want to rapidly iterate on this part and modify aspects of the design, we have to do so in cycles of 6 hours or more. This is where we can really use 3D printing to our advantage. Why not isolate the critical complex components, which in this case are the corners? Here's the updated revision of this part where we've done just that. We circumvented the anisotropy of the part with these dowels while conserving the overall geometry. If anything needs to be changed about the part, each corner unit is a half-hour print job and costs 50 cents. So you can iterate much faster on each joint if you need to, and if you'd like to change the size of the part, all you have to do is swap out the dowel pins without reprinting the corners. Here, 3D printing is perfect for this design because we've isolated the geometrically complex features. So that's the key to designing for additive. Identify what about the design can lend itself to the layer-by-layer process. This affects costs and print time, improves workflow and part functionality, and makes it easier to iterate and modify. Think about which features of a design you're working on would benefit from additive, and use that to simplify how you're creating your design. Hope this helps you get started. Happy printing.